time for us to do some practice with optimization, which really means a lot of practice with doing word problems, translating from some real-world application or real-world-ish application into mathematical formulas that we can work with and solve. And that art of translation from one to another, it's why we need to practice. It's not so easy. And it comes with doing the work. Not just seeing people do it, but actually doing it. So make sure you're doing as much as you can. And if you are following along with the video, make frequent use of the pause button. So you can say, let me see if I can do the next part. And try it yourself. And then if you need my help, unpause and I'll catch up and we'll make progress together. All right, well, we're going to be at it for quite a while. I hope you're ready. Bring some snacks in the meantime. And let's begin. Our first problem. You have discovered a discount store selling sweets in Diagon Alley. You decide to make a large purchase and ship 15 pounds of candy back to your school. Now, the chocolate frogs, which we'll denote by an F, each weigh 4 ounces, and the Bertie Bott's every flavor beans, which we denote by B, come in 12 ounces bags. After some thought, you decide that your happiness about the purchase is measured by B to the 2/3 times F. And the question, how much of each sweet should you buy to maximize your happiness? After all, we want to be happy. Okay, so we can see it's an optimization problem. It comes right here. It's the maximize. That's what gives away it's an optimization problem. And now the real question, okay, what are we doing? Well, we need to figure out how many frogs and how many beans we need to buy. That's our goal. So, well, we can start by noting we want to optimize B to the 2/3 times F. Now, the problem here is there's two things, B and F. We really need to get down to one. So either just B or just F. And there's also a lot of information we haven't used. So, for instance, we're told 15 pounds, all right, and we know how much things weigh. 4 ounces are the frogs, and 12 are the beans. All right. Now, there is, of course, one small thing we've got to be careful of, and notice they are slightly different units, so the pounds versus ounces. So we've got to make sure we don't get thrown off by that. So here we go. Let's use this information. So however many frogs we buy, the contribution to the weight of the frog is 4 ounces per frog. Now, 4 ounces is 1/4 of a pound. There's 16 ounces to a pound. So if we write it in terms of the pounds, we'll have 1/4 pounds per frog. So that's how much our weight is from the frogs. 12 ounces, well, that would be 3/4, 12 over 16. So we'll have 3/4 times our beans. That's the weight of our beans. And our total weight we know is going to be 15. Or we could say that F plus 3 times B will be equal to 60. Now at this stage, we can solve for either F or B. At the end of the day, we can get the answer either way. But we always say, what's the easier one to solve for? Now, in our case, I would say, I think it's easier to solve for F because there's just a single F. But there's also another reason. Look up here. You see how F is just a nice F to the 1? If you solve for B, you'd have something to the 2/3. I don't want to have to deal with that. So I'm going to solve for F. So that says the number of frogs we get is 60 minus 3 times however many bags of beans we get. So if we now take this expression for F and plug it in, we get that what we really want to optimize is B to the 2/3 times 60 minus 3B. Well, okay, multiply it out. This would be 60 B to the 2/3 minus 3B to the 5/3, because 2/3 plus 1. All right, well, that's not so bad. That's something we can work with. So now we have our function we're trying to optimize as a function of a single variable. So we can give this a temporary name. We can call this our function of B. All right, now maybe f isn't the best choice since it's a lowercase f, not a capital F. All right, so now taking our derivative of our function would be, well, the 2/3 comes down. 60 times 2/3, well, so first divided by 3. 60 divided by 3 is 20, times by 2 would be 40. That's b to the minus 1/3. And then bring the 5/3 down. 5/3 times 3, that's not so bad, that's 5. B to the 2/3. And, well, let's factor stuff out. They both have 5s. And I'm going to go ahead and pull out a -5. The reason I'm pulling out a negative is I see the higher power of b is negative. I want to change that to a positive. And then I'm going to pull out b, and I'm going to pull out the lower power. So I'm going to pull out the -1/3 power. So from the second part, if I want to find my new power, I take my old power, subtract what I pull out. 2/3 subtract -1/3 would leave me with a single b. Then here, I've already grabbed the b to the -1/3 to end up with 40, since I pulled out -5, says -8. Well, good news. There aren't that many possibilities. Now, one possibility is where the derivative is undefined, but that would happen at b equals 0. And what is that? Well, if b equals 0, look at our happiness. We're not happy at all. You know, we'd have 0 happiness. Okay, so that's not going to be our answer. We can throw that out by context. So that means we only have one possibility, which means it has to be the right answer. So lo and behold, we can conclude b has to be 8. So we come to the conclusion we want to have 8 of our what? Well, 8 of our Bertie Bott's every flavor beans. And then if I know b equals 8, I can take that information over to here, and I can say that f should be 60 minus 3 times 8, which is 60 minus 24, which is 36. So 8 bags of beans and 36 of our chocolate frogs. All right, and there we go. That's our answer. Cool. Nice. Now, we might pause for a second and say, are we confident we found the place where we have the most happiness? All right. Well, that's a reasonable question. And, well, we could check by looking at what happens on either side of 8. So, for instance, if I'm doing a first derivative test, I can plug in values. So here's 8. If I plug in something below 8, 7, and of course you always have to check how below. Well, just to the next critical point, which is at 0. So 7 is perfectly fine. If I plug in, what do I see? I see a negative, that'll be positive, and 7 minus 8 is negative. So there's 2 negatives, meaning my derivative to the left is positive. So I'm coming up. My happiness is increasing as I buy more beans, at least to the point where I hit 8. But what happens after that? So plug in, say, 9. 9 minus 8 will now be positive. So negative, positive, positive, which means that after 8, if I were to keep buying beans, my derivative is negative, and my happiness would go down. And therefore, yes, 8 is a maximum. Good. And there we go. Right. Real-world applications. That's what we're after. We want to have something that we can use. So the next time you swing by and you visit Diagon Alley, now you know how to maximize your happiness. Okay. On our next problem, find the area of the largest rectangle with sides parallel to the x-axis and y-axis, with one corner at 0, 0, and the opposite corner on the curve y equals 6 over x squared plus 2x plus 9. Now, you might be worried, is this denominator over 0? In other words, am I blowing up? And I'll go ahead and tell you right now the answer is no, and we'll get into that in just a second. But let's suppose we think about our picture here. I have a rectangle, and I know one corner is at 0, 0. And then I have this curve doing something. So let's say it does something like that. It's probably wrong, but okay, something, right? So my opposite corner to 0, 0 is on the curve. So here's my opposite corner. And now my sides are going to be parallel to the axis. So here's my rectangle. So we'll call it R for rectangle. All right. Now, what's our goal? Our goal is to find the area of the largest. We see the ist. All right, definitely this is an optimization type problem. So, all right, what do we need to do? Well, we need to figure out what is the area. How do you find it? Well, area is a combination of length and width because it's a rectangle, length times width. So I could say, well, if we call this x and we call this y, then what we could say is that our area is x times y, right? Well, that would mean our area would be x times 6 over x squared plus 2x plus 9. All right, good. Now, at this point, you might be thinking, Steve is suspiciously asking me and doing the noise. Something is maybe amiss here. Is this the right function for optimization? And why is it the answer maybe? So the answer is maybe, and it just depends on if you're careful. So the picture here, we've said, hey, look, put a corner over here. Here's x, here's y. Life is good. We're ready to go. But remember, that's just one possibility. Think about other possibilities. So what's another possibility? Another possibility that we should be able to account for is what if we put our opposite corner over here? So nothing says that we can't move to the below 0. In other words, what if I had picked a negative value for my rectangle? Okay, well, that's the problem. Why? Well, because notice, what is the length here? So the length would be not x, because the x would be a negative value. Lengths, measurements of distances tend to be positive. So we run into a small catch. Really, this side has length negative x, if I happen to choose a negative value for x. Now, what does that mean? Well, so one thing we can do is we can say our area is absolute value of x times y, and now this works for all values of x. But we've come at a small cost. We have to use an absolute value function. So that is one option. We can say, well, let's work with this area, which involves absolute value. And the way you would do it is to be, all right, I'll take 6x over x squared plus 2x plus 9 if I'm greater than or equal to 0, and the negatives of that, negative 6x over x squared plus 2x plus 9 if I'm below 0. Okay, so that's one option. And I do want to add, we're not going to go with that option. So it's we're going to do something slightly different. So let's go back. I did promise I wanted to revisit and say, do we need to worry about division by 0? And the answer is no. I'll just point it out really quickly. Suppose we wanted to figure out what was happening downstairs. Well, one way when you have a quadratic is say x squared plus 2x, what would I need to add to get a perfect square? In other words, I want to complete the square. I would need to add 1. And then there's still some terms left over. In fact, since I need a plus 9, and I have a plus 1, I need a plus 8. So the denominator really looks like x plus 1 squared plus 8. So that says our denominator, the smallest it could ever be, is 8. So I never have to worry about division by 0. It also says that the picture is kind of accurate in that if you think about where would the largest value be, the peak of this curve, well, it would be when you make this x plus 1 term as small as possible, because that's the only place x shows up. And so it would really peak at negative 1. So the picture is somewhat correct in the way it's drawn. Okay, so if we don't do absolute value, how do we do this problem? Well, the answer is we're going to still take our function which is going to be 6x over x squared plus 9. But we're not just going to look for the maximum value as positive. We're just going to look for the maximums and the minimums. And we're going to look at the sizes of those values. Okay, so it'll make more sense as we go along. So suppose I say our area of x is 6x over x squared plus 2x plus 9. I'm going to do another aside here to do some justification about what we're going to do. What happens as we let x tend towards infinity, plus or minus? What's the expression doing? We see that the denominator is a square, the numerator is to the first power, which means that as x gets big, the denominator dominates, the whole thing goes to 0. So we have area goes to 0 as x gets large. So, in some sense, we don't need to worry about what happens in the long, very, very large values of x. So we know something relatively smallish is what we should expect. Now, let's take our derivative, because we have our function. Take our derivative, and what would we get? Well, we get our derivative, quotient rule, we take the bottom, x squared plus 2x plus 9, times the root of the top, minus the top, times the root of the bottom. All of that divided by the bottom term squared. We know the bottom is not 0, so there's no division by 0 problems. So we're going to focus on when could we get a 0 upstairs. So working this out, what do we have? We have 6 times x squared, and then, oh, whoops, I took the root of the bottom wrong. I saw, see, the root of the bottom has an x squared, but then plus 2x. So that is plus 2. There we go. So back to our regularly scheduled problem. 6x squared, then minus 12x squared. Well, 6x squared minus 12x squared is going to be a minus 6x squared. Then you have a plus 12x minus 12x. They cancel. Good. And then you have a 9 times 6, which is, well, that's 54. All right. And, well, that's it, right? All over the bottom term squared. So, what do we get? Well, if we want to set the derivative equal to 0, we need the top equals 0, which says we really need 6x squared equals 54, or we need x squared to be 9, because 54 divided by 6 is 9, which tells us that our expression, a of x, has critical points at 3 and negative 3. All right, now let's think about what's happening. We have our picture, and I'm going to mark my points here. Negative 3, here's positive 3, and suppose we plug in some values. So for example, if I plug in 0, I see, hey, my derivative is positive. If I plug in, 100, I have a large negative plus 54, it's negative. I don't need to worry about the downstairs, it's always positive. If I plug in negative 100, same thing, it's negative. So the picture is I'm decreasing to negative 3, increasing to positive 3, and then decreasing after 3. Okay, so you might say, aha, that's it, we're done, the answer is 3. But we said we have to be careful, because remember there is that absolute value. We know that in essence what's happening is that there's a minimum at negative 3, overall minimum, and an overall maximum at 3, but now we want to say, let's ignore the signs. So that says we need to ask the questions, what happens at negative 3, and what happens at positive 3? We don't need to worry about what happens afterwards, because we know afterwards things tend to 0. And so the problem here, we can conclude, it's one of these two locations. Well, how do we figure it out? The last step for us to do is to carry out the evaluation. So let's plug it in. So if we plug in positive 3 into our area, we'd have 6 times 3, which is 18. Downstairs we'd have 3 squared, which is 9, plus 2 times 3, which is 6, plus 9. 9 plus 6 plus 9 would be 24. So we get 18 over 24, also known as, since that's divisible by 6, 3/4. If we plug in negative 3, well, upstairs we'll get negative 18. Downstairs we'll get 9 minus 6 plus 9. So 9 minus 6 plus 9 would be 18 minus 6 would be 12, which is negative 3/2. Now, we're almost done because where are we at? Well, this says if I plug in and choose the other corner of the rectangle to be at x equals 3, the area would be 3/4. If I plug in negative 3, I would get the signed area to be negative 3/2. But I get rid of the sign, so the real area of the rectangle when I plug in negative 3 would be positive 3/2. Well, 3/2 beats 3/4. So the max area would be 3/2. All right, good. All right, so in other words, because we said let's not worry about the sign, but we find both the largest positive and largest negative, and then just focus on the relative sizes, then that's where we ended up. You could have done this whole problem by coming to this part and saying, all right, let's find the critical points for the function 6x over x squared plus 2x plus 9 if I'm greater than or equal to 0, and what happens if I have negative 6x over x squared plus 2x plus 9 if I'm less than or equal to 0. And then you'd also have to check 0 as well. It would have been almost the same amount of work. Whatever makes you happy, that's what you should do. Actually, whatever helps you to understand, that's what you should do. Understanding comes first. Okay. Well, let's try another problem. So, you and some friends are going to Blips and Chits to check out their newest game, Roy 2. While you are there, you decide to spend 80 flerbos to play your 2 favorite games. Meeseek's Mansion, okay, that's going to be denoted by M, and it costs 1 flurbo per game, all right, and Crumbopulous Creed, which costs 2 flurbos per game. The games are tied together so that the total time you would spend playing the games is 1 plus root k times m plus 4k. Wow, that's quite the expression there. Determine how many times you should play each game to maximize the amount of time spent at Blips and Chits. Well, notice maximize. So we know this is an optimization problem. All right, woohoo! We're in the right setting. So where do we go next? Well, the next thing to do is figure out what we're trying to optimize. But in fact, that's kind of given to us. It's right here. This is what we're trying to optimize because this is the total time would be this, and we want to maximize time. So far, this is pretty promising. They've actually done a lot of work for us. It's nice when they do a lot of work for us. Of course, we also like to do some work too. We want to be involved in the solution. What's the catch? Well, our catch right now is we have 2 variables, k and m. We want to get down to 1 variable. So we go back and see, well, were there any other things that showed up which could help us? And they were very sneaky here. Notice they did things like spell words instead of put numbers, right? 80 flurbos. And 2, well, okay, those 2 favorite games, that's a different kind of 2. 1 flurbo and 2 flurbos. So that's information that we can use to get a nice relationship. So what do we have? Well, however many times we play Meeseek's Mansion, that's the number of flurbos we spend on Meeseek's Mansion. So we are going to spend m flurbos playing Meeseek's Mansion. And however many times we play Crumbopulous Creed, well, twice as many of that is how much we spend on it. So we're going to spend twice the k, and that's going to add up to 80. Okay, now at this point we need to solve for one of our variables, and I think it's easier to solve for m because no fraction plus I really want to avoid putting things in square roots if I don't have to. So I can say however many times I play Meeseek's Mansion, is 80 subtract 2k. So far so good. 1 plus root k, and then we have 80 subtract 2k and plus 4k. All right, well, I sense a lot of algebra in our future. Woohoo! Okay, well, let's get into it, right? So the first thing we should do is expand. All right, so we'll start by expanding here. So we'll get 80 minus 2k plus 80 times root k, and then minus 2k times root k. Well, so that would be minus 2k to the 3 halves. And then don't forget you have a 4k on the end. All right. Well, we should at least combine. And the other thing we should do is make this more calculus friendly. Now, of course, when we say calculus friendly, instead of root k, we should write that as k to the 1/2, because that's where we can use our rules in a really nice setting. And I'm also going to put the powers in order. So k to 3 halves, that's our highest power. So k to the 3 halves. And then minus 2k plus 4k is plus 2k. And then finally we have plus 80k to the 1/2. All right, so we have our function. We've gone down to one variable. Now we pull out our tools of differentiation. Okay, so we'll call this here our function. Well, since we're after time, I'll call it our function t. And we've gone down to our single variable of k. So t prime of k is derivatives. Derivative of 80, 0. Derivative of negative 2 times k to 3 halves. 3 halves comes down. We'll get minus 3. Then it'll be k to the 1/2, 1 less, plus 2. All right, and here, 80, bring the half down. That's 40, k to the minus 1/2. Okay, cool. So, well, we definitely have a problem if k equals 0. So you'll notice at k equals 0, I'm going to have what? It's an undefined. Okay, so k equals 0. That's a potential place. We'll keep that in mind. We'll come back and visit that. So this is t prime undefined. There's nothing that rules it out. See, if k equals 0, you can still play quite a bit. See, if k equals 0, that says you're not playing Crumbopulous Creed at all. So you're going to be playing your Meeseeks Mansion nonstop. Well, that gives you time, and maybe Meeseeks Mansion takes a lot of time to play. So it could be that's the best thing to do. Or maybe not. All right, so we continue. So now what? Well, next thing is we got to solve for when does this equal 0. And at first glance, it doesn't feel very promising, does it? Because it doesn't feel like what we want. At this point, we're like, wait, shouldn't there be a quadratic? I thought we'd always get quadratics. I was getting good at them too. Don't worry, there's a quadratic coming. Well, let's see how we get there. Let's start by pulling out the smallest power of k. So, and I'm going to pull out a negative as well. So this is negative. I'm going to pull out k to the negative 1/2, which would say, the reason I'm pulling out a negative is I want a positive coefficient in front of the largest power of k. Now, here's where it's going to get fun. If I pull out k to the negative 1/2, so I'm pulling out k to the negative 1/2 to the front, I had k to the 1/2. What's the new power? Well, the correct answer is k to the 1, which is, a half plus a half. Bear with me. Let's think of that as k to the 1/2 squared. You'll see why. All right, the next term, 2, there wasn't a k anywhere, so it's like 2k to the 0. I pulled out a k to the negative 1/2, and, oh, it's not a plus because I'm putting out a negative. Let me fix that. Minus 2k to the 1/2, and then on the end, well, minus 40. All right, now, what do you notice? The reason I wanted to do that was because I was anticipating. Oftentimes when I see 3 terms, I'm like, well, could there be a quadratic hidden there? And I said, oh, like I would have a k to the 1/2, and a k to the 1 is k to the 1/2 squared. So if you think of this, we can give it a name like x. So it's like x squared minus 2x minus 40. All right, so that, when we write it in that form, x squared minus 2x minus 40, we feel more comfortable about that. So we say, okay, whoops, I forgot. Oh my gosh, check. I forgot about that 3. Okay, so that's really a, there we go. Now I fit it in. Okay, yeah. Copying mistakes, they're actually, the further you go, the more often that the mistakes you make tend to become copy mistakes. So it's good to double check and making sure that you're copying everything down right. Okay, so what are we looking for? Well, if this does factor, what would have to be true? Well, 3x, there's only really one way to factor, 3x and x. So we have to think about ways that we can factor 40. Now, well, there's a lot of ways, but we need to make sure we end up with something where we combine together to get a minus 2. So one of these will be a plus, one of these will be a minus, since that's a negative. Well, a little bit of trial and error here. Let's think about 40. What's true about 40? Well, 40 is 1 times 40. Well, no, I don't think so. There's not really much you can do there. It's also 2 times 20. Well, that's a little bit too big, I think. 4 times 10. Well, 4 times 10. Notice, hey, what about this? 3 times 4 is 12. 1 times 10 is 10. And 12 and 10 differ by 2. Okay, all right, that's promising. So what would that need to be? Well, let's see. If we want to end up with a negative 2, we should make the 12 negative. So that means x minus 4. And here it would have to be the other part, so plus 10. Okay, let's check. 3x squared, that's good. Minus 12x plus 10x, good. Minus 2x and minus 40. Okay, good. Okay, so now let's see what that says about our derivative. It says, lo and behold, we have our minus k to the minus 1/2, and then we have 3 square root of k plus 10, and then we have square root of k minus 4. All right, so that's what we have. Now, where would our derivative equal 0? Well, can I have 3 root k plus 10 equals 0? Well, no. That's not going to work. See, if I had 3 root k plus 10 equals 0, what would that mean? It would mean that this would tell us that root k is negative 10 thirds. And when we talk about the square root function, the square root function means the positive square root. It is true if we take the square root, there's 2 potential answers, but when I say the output of the square root function, it's always a positive output. So that's not going to be a possibility. That can't happen. So what can happen is we can have root k equal to 4. All right, so if root k equals 4, what does k equal? Got to get rid of the square root. And the answer is k equals 16. Okay, so this is where t prime equals 0. Good, good. Now, we have some possibilities. Let's use our first derivative test, because, I don't know, second derivative looks like it would be a little bit tricky to play with. First derivative, we can do that. So we draw our number line. We have 0, we have 16. And 0 really is a boundary, because we can't really play a game a negative number of times. It's not like I can go to the arcade and say, well, I'm really bored. You owe me the cost of playing this game. And if we plug a convenient number between 0 and 16, well, 1 is between 0 and 16, and 1 is very convenient. So 1 to any power is 1, so it'd be negative 3 plus 2 plus 40, which means my derivative is positive. Okay, so that my time spent playing increases from playing no games of Chrombopulus Crete, at least up until the point I got to 16 games of Chrombopulus Crete. Okay, now suppose I just really love Chrombopulus Crete and I keep playing. Well, so what's a convenient number above 16? And they might be thinking like 17. Well, but keep in mind, we have square roots involved. Okay, how about 25? 25 is good because it has an easy square root. So if we plug in 25, square root of 25 would be 5. So negative 3 times 5 is minus 15, plus 2 gets us to minus 13. And here it'd be 40 over 5, which is 8, which gets us to, well, 8 plus 2 is 10, minus 15 is minus 5. So our derivative is negative above 16, which means that as we move towards 16 games, our time spent playing is increasing, and then after that, our time spent playing is decreasing. So we should definitely shoot for 16 games of Chrombopulus Crete. All right, so we're ready. And now, what's our answer? Well, we have to find how many times should we play each game. So we should say we can play K 16 times, Chrombopulus Crete 16 times, and Meeseek's Mansion, well, now plug in the 16 here. So if we plug in 80 minus 2 times 16, well, that's 32. 80 subtract 32 gets us to 48. All right, so that's what we should do. All right, sounds like we're going to be playing still quite a fair amount of games. We'll have a lot of fun, lots of fun. Okay, cool, good times, good times. All right, on to another problem. Of course. So, you are given a wire of length 68 centimeters. So sort of here's the wire. And what we're going to do is we're going to pull out our scissors and do a cut. All right, so we've now cut the wire into pieces, and then we're going to bend the wire into a square. So here's a square, and the other into a rectangle. And in the rectangle, it's not just any rectangle, it's a case that the length here is twice as long as its width. So the question, find the minimum possible total area enclosed by the figures. Okay, and of course it says, demonstrate convincingly that your answer is indeed the minimum. All right, so that really says, hey, let's run a test and verify it is a minimum. And then, of course, there's this side comment. It is possible the entire wire is used for either shape. Now, what does that mean? Well, you can think of it saying, hey, I could take the wire and instead of cutting it, I'm just going to say, look, just make it into just a square, or just make it just into that rectangle. And therefore, we would make these nice little shapes. And so, in some sense, what we're saying is, don't forget about the boundary. Because whenever you're doing an optimization problem, there's a natural boundary condition put in. All right. So it walks us through an example, and it says, hey, here's an example. This has length 44, and 24 is where I cut, so I get 11 by 11. And see, it's going to be 11 by 11 because I have to take the 44 and I have to make the 4 sides of the rectangle. So each side is 1/4 as long. All right, and then the 24, that would go into one where I have a 4 and 8. And we can check, well, 4 and 8 plus another 4 plus another 8 does equal 24. And it even does the computation for us, and it says, hey, look, the area of this configuration is 153. Now, whatever our final area is, we better be below 153, because if we are not below 153, we made a mistake, because it says we know 153 is possible. It's probably not the right answer, by the way, but okay. All right, but to get started, we should say, of course, this is an optimization problem because we see the word minimum. And what are we minimizing? The total area. So let's think about what's true. What can we vary? Well, what's going to happen is we're going to make a cut. So we're going to cut somewhere. So what we can vary is where that cut gets made. So now we start thinking to ourselves, we should come up with a name for where we make the cut. So one thing we can do is say, all right, let's say whatever this length is, we'll call it X. So 44 is just a potential choice for x, but it doesn't mean it has to be 44. Now, what about this length? We could call it y, but automatically we know what it is, right? Because we know the total length is 68. And we said the first part, this first piece over here has length x. The total length is 68. So the remaining part would be 68 minus x. All right, good, good. Now, we keep going. So, let's go a little bit further. So for the first one, where we turn it into a square, well, the area of the square would be done by the following. It would be 1/4 x times 1/4 x. And where is the 1/4 coming from? Well, because I have to divide that length into 4 equal-sized pieces to get the pieces of the square. Okay. Now, that one was the easy one. Let's get to the rectangle. And that one we should pause for a second and really think about what's going on. So, what do we know? Well, in the square, we had these sides were equal. And so we said, okay, everything gets proportioned equally. But in the rectangle, it's not that these sides are equal. In fact, they're not equal. And so I don't just divide the total length by 4. I have to say, well, I have to proportion things correctly. So let's think about what we have. If I think about my total length and how do I proportion it, well, what would I do? I can think of it as, let's for a second just give a temporary name. We'll call this L, and then this would be 2L. So what's the total perimeter? Well, L plus 2L plus L plus 2L. So what I get is that the perimeter would be equal to 6 times L. So if I want to know what L is, I divide whatever the total length is by 6. So see how that works? 24 divided by 6 gives me 4. Okay, good. So now what do I have? Well, this length here will be 1/6 of 68 minus x. So 1/6 times 68 minus x. Ooh, I'm already regretting my choices, but that's okay. All right, now the other length here will be twice that long. So that'll be 2/6, 68 minus x. Okay, so the total area. The reason I say I'm regretting my choices is like, do I have to deal with 68 minus x squared? Maybe, but maybe not. But the total area will be what? We'll call it total, and it's a function of x. 1/4 x times 1/4 x would be 1/16 x squared. And now, here, it's 1/6 times 2/6, but hey, 2/6 is really just 1/3. So that'd be 1/6 times 1/3, which would be 1/18. 68 minus x squared. Now, do we need to expand? I don't think so, because I think we'd probably get lost in the weeds trying to multiply 68 times 68. And in essence, we don't need to, because we're not after really what's happening with the function. The real question is what's happening with the derivative. So, what would t prime of x be? Well, take our derivative. 2 comes down. 1/8 x. Plus, here, 2 comes down. 1/9. And then it would be 68 minus x, and, being careful, what else? Times minus 1. Do you see where that minus 1 comes from? It's the chain rule. Root of the inside, because I'm doing 2 comes down, 68 minus x times root of the inside. Okay, so, well, that's it, right? Okay, well, that's actually a nice function. Now, the next thing we need to do is set this equal to 0 and figure it out. It's never undefined. It's really clean function. Okay, so let's multiply by enough to get rid of our fractions. So I want to multiply by a number big enough that when I multiply it, it's divisible by 8 and divisible by 9. 72 will do it. So multiplying everything by 72 gets us 9x, and then minus 8 times 68 minus x. Okay, so far so good. That's still equal to 0. Of course, we can multiply this out. So 9x minus minus makes a plus 8x. 9 plus 8 is 17x. And 8 times 68, I'll leave it as 8 times 68. Hopefully something nice happens. That can move to the other side is 8 times 68. Now, if we have any hope of this being a nice number, something has to be divisible by 17 because it's a prime number. Well, 17 does not divide into 8. Does 17 divide into 68? It does, right? 17 times 4 is 68. So what we really have is that this is 8 times 4 times 17. Cancel the 17s, and we get x should be 32. All right, so we now have a candidate. Okay, so x equals 32. Now you might ask, is that a min or a max? Well, because we want to find the minimum, we don't want to accidentally find a maximum. Well, that would be terrible to do all that work and find the wrong thing. So let's do our second derivative really quickly. So the second derivative, well, here we have derivative of 1/8 x is 1/8. And now, what's left? Well, minus minus will make this a plus x times a ninth. So this will be plus a ninth. And that's a positive value. Doesn't even depend on x. So definitely, if we found a critical point where the derivative equals 0, which happens at 32, because our second derivative is positive at that point, it's a minimum. So, good. We know it's a min. So we'll make a little note here. By the second derivative test, this is a min. All right. Now, but we're not done yet. We have done the demonstrate convincingly that the answer is the minimum, but we're after the minimum possible total area. So the last thing for us to do is to plug 32 in. Now we could plug it into here, but maybe it's a little bit easier to see what's happening here. So we know x is 32. 1/4 times 32 would be 8. So our square is 32 by, our square is 8 by 8. So we get our square is 8 times 8, which gives us 64. Our rectangle, well, we're going to take 68, subtract 32. And if you take 68, subtract 32, you get 36. 36 divided by 6 is 6. So it's going to be a 6. And then here, it's twice as big. So it's 6 times 12. So there we go. That's going to be the size of that. All right. Well, 6 times 12 is what? It's 72. And if we add those up, we end up with 64 plus 72 is 136. And we can even put it together, centimeters squared. And so that is smaller than 153. Phew. If we had gotten something larger than 153, we definitely would have made a mistake. All right, so there we go. Oh, nice. Good, fun stuff. Okay, well, on to another problem. Okay. You find yourself living in Bikini Bottom and want to test your entrepreneurial skills. You decide to set up a small business selling food from the Krusty Krab near the beach. You'll have 2 items, the Krabby Patty, which we'll denote by P, and kelp fries, F. You have to first purchase the food and then resell them. So given that you have $14 to purchase your supplies, a Krabby Patty costs $2, an order of kelp fries costs $1, and your return will be 1/10 p squared times f plus p. It looks like you really have to have a Krabby Patty to make any money. All right. And anyways, okay, determine how many of each type of item you should purchase. All right, we've done a couple of these already, so hopefully we're sort of got the mood for it, right? We have a pattern here. We know what to be going on. So we say, okay, we know we're trying to do an optimization, right? Well, it doesn't explicitly state optimization, but I suspect you want to make money, right? Most people who do want to make money don't set out to say, how can I lose money? So our goal is, how can we make the most money? Okay, well, that's a good question to ask, and of course a great question to answer. So we want to make sure our return on our investment, that's what we want to make large. Because, well, we like to be able to pay things like rent. Okay, so that's what we're trying to optimize. Well, of course, two variables. Let's knock it down. We have to pay for our supplies. So we have $14, and we have to split it between our patties and our fries. All right, so we could say, well, we have 2 times our patties, because that's $2 per patty, plus 1 times our fry, $1 per fry, has to get to 14. So we do our traditional, hey, let's solve for one of our variables, and we can solve for either one. But I think f is easier to solve for because, well, I don't like fractions. I try to avoid them as much as I can. All right, so 14 subtract 2p. So this can become 1/10 p squared times 14 subtract 2p plus p. All right, good. Well, what comes next? Well, we need to expand. We don't need to, but I think it's easier. It's easier to expand than to try to do some product rule when we're taking derivatives. So we have, all right, 14/10. Well, 14/10 is another way of saying 7/5. So 7/5 p squared. Then 1/10 times 2, 1/5, and then p squared times p makes p cubed, and then there's a plus p. Okay, so this is our return on investment. Well, let's call it r for return. So we'll call it function r of p. So take our derivative, r prime. I should have said r prime. Okay, so r prime of p. So what do we get? Take the 2, comes down 14/5 times p, and then here minus 3/5 p squared and plus 1. Aha! Yeah. Another quadratic. Okay, good. Well, we're going to get good at these, right? That's the goal anyways. Okay, so let's pull out a negative 1/5 because I want to get rid of my fractions. It's easier for me to figure out how to factor when there's no fractions. And I want to make the p squared be positive. So let's see, that's negative 1/5. And if we pull that out, we get 3p squared. And then minus 14p and minus 5. Good. All right, so there we go. And of course the 5, because we pulled out a 1/5 out of the 1, so that's why we need it to be 5. All right, now, does this factor? Ha ha ha. We strongly suspect it does. I am sorry. I'm going to apologize in advance if you have problems that don't factor. But quadratic formula still works, and that's okay. No problem. So, can this factor? Well, we'd have to have 3. Not a lot of ways to factor 3. So 3p and p. And 5, not a lot of ways to factor 5. Just 1 and 5. So I could put the 5 here, or I could put the 5 there. But to get to 14, which is not very far from 15, I better put the 5 there. And then finally we have to say, well, this is negative, so one of these is a positive, one of them is a negative. I want to get negative 14p, so I better make sure that the thing which involves 3 times 5 is negative. So I think this is it. Now, of course, we don't want to just think it's it. Let's check. 3p squared, Okay, minus 15p plus p, good, minus 14 and minus 5. All right, well that says, hey, we have some possibilities. Negative 1/3. Well, I can't buy negative 1/3 of a patty. It's not like I'm walking in with 1/3 of a patty in my pocket. I'm going to slap it on the counter and say, okay, here you go. Take 1/3 of this patty. It's not how businesses work. So that's not going to be it. So the other case, p equals 5. All right, that we can do. We can buy 5 patties. All right, so we have our candidates. So it looks like p should be 5. And if p is 5, 14 subtract 2 times 5 says that f should be 4, right? 14 subtract 10, 4. All right, and there we go. That's how many of each type we should purchase. Now, we should check a couple of things. First off, are we indeed at an optimum place? Well, we can do some various things. If we were to, say, apply the first derivative test, I don't know if one of them will be any harder or easier than the other. So remember the first derivative, there's a negative 1/5 here, and we have 5. So the question is, should I operate on either side? Well, if I plug in 4, what do I see? I see a negative, a positive, and a negative. And so that says that R prime is positive, which means that if I buy less than 5 patties, I'm better off buying more because I'm increasing before 5. If I plug in something after 5, say like 6, I'll see a negative, positive, and a positive, which means that my R prime is negative, which means that after 5, I'm getting a worse return on my investment. So if I'm trying to maximize my R of P function, which I do, then I should choose 5. So 5 is where I should invest. Now, you might ask another question. How much money are we going to make? Well, we can actually figure that out too now because we know 5 and is P and F is 4. So let's see, we're going to get 1/10. P squared would be what? 25. And then F would be 4. And we're going to add 5. So 25 times 4 is 100. 100 divided by 10 is 10. 10 plus 5 makes 15. Okay, so we're going to get a return of $15. Well, how much did we put in? We put in $14. So, should we do it? Yeah, we make $1. We're ahead. Of course, maybe it feels how much work it feels to get that dollar. It may not feel like we're ahead, but okay, good. Well, invest $1 at a time. That's how you can make money, right? All right. Another problem. You're conducting an experiment, and to help minimize the risk of the process, you need to find the minimum average rate of change for the interval 0 less than or equal to x less than or equal to a, where a is positive, for the function f of x, which is 2x to the fourth minus 3x cubed minus 36x squared plus 42x plus 250. Like, wow, that's a lot. Okay. Now, we can see this is an optimization problem, and not every word problem is an optimization problem. So that's why I keep emphasizing we can see this is an optimization problem. We want to make sure we can recognize problem types because it's good to know what type of problem we're doing before we start the problem. The minimum, of course, is what makes this an optimization problem. We know we're trying to find a minimum. So what do we need to minimize? Well, the thing that we're minimizing is the average rate of change. So, this is good. It helps do a little bit of a callback. So the average rate of change over an interval would be what? It's how much our output changes. So it'd be f of a subtract f of 0, and then divided by how much the input changed, a minus 0. Okay, so that's our average rate of change. So we're going to plug in f of a, that's 2a to the fourth, minus 3a cubed, minus 36a squared, plus 42a, plus 250. Okay, that's what happens at a. subtract what happens at 0. Well, 0 is very convenient. 0, 0, 0, 0, 250. So subtract 250. And that's all divided by a. All right, well, hopefully something nice will happen. A little bit nice happens. The 250s cancel. That's good. But then, if you look at what's left, everything that's left involves a. Since everything involves a, I can divide. So, what do we really have? We have 2a cubed minus 3a squared minus 36a plus 42. Okay, so here's our average rate of change as a function of a. This is what we're trying to optimize. Not the original function. This is not the function. This part, if we tried to optimize that, we'd get some crazy numbers. We're trying to optimize the average rate of change. So that's what we're really trying to optimize. Okay, so we should think about what to call this. Well, we can't call it f. Well, I don't know, g? Sure, why not g of a? So take our derivative, g prime of a. We'll get 6a squared minus 6a minus 36. Okay, well, factor out a 6. 6a squared minus a minus 6. And, another problem that factors. Good. Well, so that's 6. And then, what do we see? I need two things that multiply together to give negative 6, but when added, give negative 1. Well, I think minus 3 and plus 2 fits that. Well, let's check. A squared, good. 2a minus 3a minus a, and minus 3 times 2 is minus 6. It works. Woohoo! Nice. Okay, so what do we need to do? Well, there's no place where it's undefined. So we could say, all right, what causes this to be 0? Well, that's a good question. And we can spot, hey, here's a possibility, negative 2. And here's another possibility, positive 3. Now, we can rule one of these out right away with no work at all. And why? Which one? Well, the negative 2 is out. You might say, well, what's wrong with negative 2? We're looking for something which is positive. Negative 2 is not. So that's not going to be the place where we have a minimum. Okay, which means we have a candidate. And so, what are we looking for? You are conducting. You need to find the minimum average rate of change. Okay, so we're not looking for the value for A. What we're really looking for is what happens what is that minimum average rate of change? So we're looking for our result when we plug 3 in. Okay, so what we think is the minimum will be g of 3. Well, that's 2 times 3 cubed minus 3 squared. Subtract 36 times 3 and add 42. Well, that's a lot of work. Whoops, I forgot a 3 times. So there's another 3 here, right? So 2 times 3 cubed, 3 times 3 squared, 36 times 3, and 42. Well, if I take 2 times 3 cubed, this is also 3 cubed. So this is really 3 cubed, which is 27. Here, 36 times 3, 108, of course, as we all know. And plus 42. 42 and 27 make 69. 69, subtract 108, would get us to negative 39. Okay, so that is what the answer should be. We should be careful. We haven't shown it's actually a minimum yet. So let's just quickly check that it's a minimum. And how do we do that? Well, to check that it's a minimum, we'll go ahead and do a quick second derivative test. So g double prime of a would be 12a minus 6. So g double prime of 3 would be 36 minus 6, which is 30, which is positive. And so second derivative test, if you remember, when the second derivative is positive, our curve looks like that, and so it is a minimum. All right, cool. All right, we did it. Woohoo! Good times. Now, other than the arithmetic at the end, nothing too bad. Nothing too bad. Okay, so on to another problem. Okay, here we go. So let y equal 1 over 1 plus x squared. Find the value a greater than 0 where the y-intercept of the tangent line at x equals a is maximal. Well, okay, this will be interesting. So what's going on here? Let's see if we can get a handle on what's occurring. So I have the function 1 over 1 plus x squared. Now, if you look at what this function looks like, it has this sort of nice shape. It goes up, and then it comes back down. So it's almost a bell shape. Now, what's going to happen is at any given point on this curve, I can take a tangent line. So I could do a tangent line down here, and I could say, all right, where does this tangent line intersect on the y-axis? Well, it depends, right? So here, if I take this tangent line here, it looks like it's going to intersect there. But if I take a tangent line further back, it looks like it might be lower. If it looks like if I can move a little bit closer, it looks like it'll be higher. So it depends where I take my tangent line. Okay, so now we have an idea. We can see it's an optimization problem, of course, because it's maximal. And we say, well, what is it we're trying to maximize? Well, the y-intercept of the tangent line. See, this is what we're trying to maximize. So, first step is let's find a formula for the y-intercept of the tangent line. So it's helpful to sort of walk our way back and say, okay, let's do a quick review. What does our tangent line look like? So the formula for our tangent line, just generically, has the following form. So y equals the value of the function at a plus the derivative at a times x minus a. And if you rewrite this, you get y equals the derivative at a times x plus, and then you add your constants, which would be f of a minus a f prime of a. So this part right here, this is our y-intercept, where this part up here, 1 over 1 plus x squared, this is what I'm calling f of x. All right, so now we kind of have our pieces in place. So let's make some notes here. So f of x is 1 over 1 plus x squared. You can think of it as 1 plus x squared to the minus 1. So f prime of x would be chain rule, minus 1 comes down, 1 plus x squared to the minus 2 multiplied by the root of the inside. So multiplied by 2x, which can also be written as minus 2x divided by 1 plus x squared squared. All right, so we're almost to the point where we have our function. We just have to put our pieces together. We know what our function looks like, we know what the derivative of our function looks like, and we know what our y-intercept looks like. So our goal here is we're trying to optimize the following. So we want to optimize the expression. I'll call it g as a function of a. And I'm just going to copy what we have, f of a minus a f prime of a. Well, that is f of a, 1 over 1 plus a squared, subtract a. Now, f prime of a would be minus 2a over 1 plus a squared squared. All right. Well, let's combine fractions together. And, what would we get? Well, this is almost the same, right? It's just that here, this term is being squared. It's not squared there. So I'd have 1 plus a squared, because I multiply top and bottom on the first term by 1 plus a squared over 1 plus a squared. Good. minus a minus 2a makes a plus 2a squared. Divide that by 1 plus a squared squared. Or 1 plus 3a squared. Divide that by 1 plus a squared squared. Okay, that's what we're trying to optimize. So, what's our next thing to do? The next thing to do is take the derivative of what it is we're trying to optimize. All right, well, we keep going, and hopefully we'll get there. Of course we'll get there. No problem, no problem. So, here, it's a nice rational function, which means polynomial over polynomial. So, it's a good candidate to use the quotient rule for. So, g prime of a. So, we're going to take the bottom, 1 plus a squared squared, times rid of the top, 6a. Subtract the top, 1 plus 3a squared, times rid of the bottom. Well, 2, 1 plus a squared to the 1 times 2a. All of that divided by the bottom term squared. Well, squared squared makes it 1 plus a squared to the 4th. Okay, good. Okay, now we can see a little bit that automatically simplifies because every term involves a 1 plus a squared. So we'll cancel a single 1 plus a squared off of every piece. So that gets rid of that one, gets rid of one of those, and then we reduce it to 3 downstairs. All right, well, after that, well, keep going. Okay, so multiplying that out. We're going to get upstairs, we have 6a plus 6a cubed. All right. And then minus, and remember the minus is going to go through to both terms. There's also a 2 and a 2a on the end. So minus 1 times 2 times 2a, so that's minus 4a. And then minus 3a squared times 2 times 2a would make minus 12a cubed. All of that, divide that by 1 plus a squared cubed. All right, good. Okay, now, we're getting closer. I can feel it. We're almost there. It's exciting. Okay, 6a subtract 4a is 2a. 6a cubed subtract 12a cubed is minus 6a cubed. And downstairs, we'll get 1 plus a squared quantity cubed. Well, upstairs, we can pull out a 2a. So 2a, and then we'll have what? 1 minus 3a squared. And then downstairs, we'll get 1 plus a squared cubed. All right. Good. Now, we're after the critical points. Is this ever undefined? Beautiful function. Is this ever 0? Well, at a equals 0, now that won't work. I need a to be positive. So, the only thing that could happen is if 3a squared is equal to 1. Okay, well, suppose for a second 3a squared equals 1. That really says a squared is a third, which says what? A is 1 over the square root of 3. Anybody said, wait, plus or minus? Remember, a is positive. So I can't have a be negative. So that's our only candidate. So if we only have one, that's got to be our right answer. So our answer is 1 over root 3. It does make sense, of course, that we should only expect one answer. We can see that as we're far away, or we have very shallow tangent lines, it won't go, it'll hit below, and we're increased, and then as we hit the top, we start to move down as we head on down. We could do a derivative test, but I'm going to skip that part. Instead, I want to just point out something kind of interesting, because you might be saying, wait a second, I've spent a lot of time with 1 over 1 plus x squared. 1 over root 3 sounds really familiar. Do you recognize what it is? It's not just a random value, or if you will, a random point on this curve. There's something going on with this particular value. It is where there's an inflection point. Now, you might be saying, coincidence? To which I respond, I don't think so. Okay, so let's sort of dig into why it might not be a coincidence. So let's come back up here and just talk about generically. So here's our y-intercept. Let's just take the derivative of this. So if you take the derivative of the y-intercept, what would you have? You'd have f prime of a. Here, product rule, so the derivative of the first would be 1. So then you subtract f prime of a, and then minus a f double prime of a. So you see the f prime of a's cancel, and what you end up with is you minus a times f double prime of a. So that when you're looking at the y-intercepts, where are they maximized or minimized? Well, the answer boils down to either at 0, which is the a, or at an inflection point. So that's why, aha, it was an inflection point. So, okay, good. Fun times, fun times. All right. Whew. Well, another problem, right? There's always another problem. So, for an angle, theta, where it goes between 0 and pi halves, take the ray going out of the origin that forms an angle of theta with the x-axis. So here's where theta is in the picture. And the ray hits the unit circle. So this part right here, this is the unit circle. Okay, so where that ray, so here's the ray coming out, we draw a tangent line. Okay, now, what is A? A is the region which is above the ray and inside the unit circle. So it's this darker shaded pi. There's an A here. It's a little bit harder to see because of the coloring, but this is A. And let B be the region which is below the tangent line here and below the ray and outside the unit circle. So it's this shaded region here. So here's A, here's B. The question, determine the minimum value of the following. 3 times the area of B plus the area of A. All right. Well, interesting. That's, All right. Well, we can see minimum, so we know it's an optimization. And we can see here, there's kind of a trade-off, right? Because if I try to make the area of A small, that would say I want to move my tangent line up. That would make the area of B quite large. If I try to make the area of B small, then that starts to make the area of A larger. So this is a classic optimization where there's trade-off coming into play. How do I balance the area of A versus the area of B to give me the best possible result? Well, the answer is, of course, carefully. So, okay, So we need to start thinking. So really, we should think about what's our variable. What is it we're trying to use to make our decision? And they've already kind of given to us what we should key off of. We should work off of theta. So theta is where we're going to build our expression here. So we need to figure out how can we find the area of our pieces in terms of theta. And then we'll put it all together, and hopefully we'll have a nice little answer. All right, so let's explore for a little bit. All right, so we can say the area of a wedge of a circle of radius r with central angle alpha is 1/2 alpha r squared. So one thing we can conclude is that this piece right here, this unshaded piece, so this wedge right here, this has area 1/2 times theta. The r squared is 1 because the area is just, the radius is just 1. It's a unit circle because it said unit right here. Unit circle means r equals 1. All right, so unit circle, all right. Okay, so we know the area there, and so that's useful. Let's try to tackle another question. Suppose we wanted to find the area of this triangle. So how could we do that? Well, what's true? Now, it's not just any kind of triangle, it's the right kind of triangle. So in particular, this side right here, this is a right angle because when I take a tangent line to a circle, it's going to be perpendicularly intersecting. It's a unit circle, which means that this side has length 1. So this side has length 1. if I think of that as the base, if I knew the length of this side, then I'd be in great shape. Why? Well, because the length of this side would be the height. And then if I have base and height, I'd have my area. So, I have an angle, I have the adjacent side, and I'm after the opposite side. What connects all these pieces together? What connects them together is the tangent. All right, so we can say that, let's call this opposite side, we'll call it h for a second, h for the height of this right triangle we're forming. So we can say tangent of theta is equal to the opposite over the adjacent, which is h. So I can say that the area of this triangle is equal to 1/2 times the base, which is 1, times the height, which is tangent of theta. So we're now ready to find what is b. So I can say that the area of b, that's not so bad, that's equal to, I take the big triangle, which is 1/2 tangent theta, and then I subtract this little piece here. So I subtract 1/2 theta. All right, so that's the area of b. So the triangle, subtract the wedge. Now the area of A is actually the easier one, because how can we think of the area of A? Well, for A, we can say the following. I can take 1/4 of the circle, then subtract off this little wedge. So the area of A, well, 1/4 of a unit circle is area pi r squared, so it's pi. So 1/4 pi, and then we're going to subtract this little piece here, 1/2 theta. So again, it's the quarter circle, subtract that wedge. Okay, so there's my area of A and my area of B, all expressed in terms of theta. So we put it all together, and now we're going to have a single variable function that we can actually do something with. Okay, that's great. We like to get to that stage. So this is equal to 3 times 1/4 pi minus 1/2 theta, and then plus 1/2 tangent theta minus 1/2 theta. Okay, so we got to just work our way through here. We have the 3 pi 4s. Okay, so that's just going to be fixed for now. Doesn't change. Here we have minus 3/2 theta minus 1/2 theta. So that's minus 4/2 theta, which we can say is minus 2 theta. And then we have plus 1/2 tangent of theta. Okay, so there's our function. This is the function we're trying to optimize. And so let's call it our area as a function of theta. Okay, well, probably shouldn't use A because A is for that little wedge. Okay, so we'll use our f as a function of theta. There we go. There we go. It's bad form to use the two things represented by the same symbol because it's easy to confuse the two. So let's try to avoid that. Now we're ready. We have our tools in place, right? We did the hard part. The hard part about these problems is the setting things up. We just finished that part. So woohoo, we made it over the hump. All right, it's all coasting downhill from here, I hope. Okay, so we take our derivative. F prime of theta. Well, the derivative of 3 pi 4 is 0. Derivative of negative 2, theta, negative 2, plus 1/2. And the derivative of tangent is secant squared theta. We'll set that equal to 0. Okay, that's all right with us. So that says what? 1/2 times secant squared theta needs to equal 2. Or, if you like, secant squared theta should equal 4. Or, taking the square root, secant of theta should equal 2. Now, you might say, hey, do I need to do plus minus? We actually don't need to do plus minus because our angle is between 0 and pi halves. Since our angle is between 0 and pi halves, the value for secant in that range is always positive. So we can't get a negative value for secant. So we're okay sticking with just positive 2. Good. So now we know secant of theta equals 2. Do you remember what's the arcsecant of 2? Okay, that one's maybe tricky. But maybe you remember that secant is 1 over cosine. So let's flip both sides. So saying secant of theta equals 2 is the same as saying cosine of theta is equal to 1/2. Now, that one maybe is a little bit more familiar. If you're thinking in terms of the unit circle, so maybe it's not so surprising we see a unit circle showing up, the cosine corresponds to the x-coordinate. So we're looking for a place where the cosine equals 1/2. Well, that angle right there is 60 degrees or pi thirds. So, we have a single candidate, pi thirds. And that should be the answer. Now, if you were being cautious and say, are we sure? Well, take the second derivative. See, in the second derivative, -2 goes away. So if we were to take the second derivative of theta, we would have f double prime of theta. We get 1/2 times 2, which is 1, which is secant theta, and then times the derivative of secant by the chain rule, secant tangent. But when you plug in pi thirds, the important thing is that all of these numbers are positive. So if you multiply them together, we still are positive, and therefore, at pi over 3, this is a local min. Okay, whew, good. Now, are we done? No, not quite. What we've done is we figured out for what choice of theta do we have a minimum area. But what were we asked to find? What is the actual minimum area? Not when does it happen, but what is it? So we're almost done. So the last thing for us to do is to plug in these values and see what we get. So when we plug in pi thirds, we get that the area here, I'll try to squeeze it into the side here. So the area will be 3 pi fourths, is just 3 pi fourths, nothing to do with that. And then we're going to subtract 2 times pi thirds, so subtract 2 pi thirds, and then plus 1/2 tangent of pi thirds. Now, tangent of pi thirds, that's something we actually know. This is root 3. Now here, you'd like to combine those together, so you'd say, oh, I can do them as 12ths. So, if I want 3 pi fourths, I can think of it as 9 pi 12ths, 2 pi thirds as 8 pi 12ths. So together they make pi 12ths, and then plus 1/2 root 3. And that's the answer. Wow. It's kind of an amazing answer, actually. It's such a beautiful, everything's set up just right, so it works out. This is a fun problem. I like this one. I like a lot of problems. As you have come to discover, I like a lot of problems. All right, good. Well, good news is we still have more problems, so there's a lot more for me to enjoy. All right. Find the point on y equals root 2 over 2 times x squared nearest to the point -6 comma 4 root 2. All right, well, what is that saying? Well, what's going on here? We have a curve. Now this curve, if you didn't see the root 2 over 2, you say, hey, that's a parabola. Well, what happens when you add the root 2 over 2? The answer is, hey, it's still a parabola. But what happens is it just scales it vertically. So we have this parabola opening in some sort of upward motion. It's being squashed a little bit, but not terribly so. Okay. And now there's this point, very curiously described. And this is the point at -6 comma 4 root 2. And now the question is, look, there's lots of points on the parabola. Among all the points on the parabola, which one is somehow closest to it? So that's our goal, is to say, where's the point which are closest to it? We can see optimization because we see the est. When you see est, that's optimization. The fact that we see something like near, that means there's a distance involved. So this problem is really about optimizing distance. All right, well, let's begin. So the first thing we should do is start setting up our function. Now, in some sense, we have a pretty good start. We know what we're looking for. We know it's the distance. We have the distance, one point is minus 6, 4 root 2. The other point here, well, that would be some x to be determined. And the y, well, we're on this curve. So the y value is root 2 over 2 x squared. All right? So now we say, well, great. Let's just find the distance between those points and see what happens. So we have our distance is the square root of, we take x minus 6, so x minus 6 is x plus 6 squared, plus root 2 over 2 x squared minus 4 root 2 squared. All right, there's what we have. Okay, good. Now, good news, it's a function of a single variable, so woohoo, good for us. Let's clean it up a little bit. Now, the big thing we want to clean up, there's one part which is kind of unpleasant here, and I think we all know what we're looking at. The square root. The square root is a challenge. In fact, a big part of Calc 2, we'll spend at least a day or two on this, is the exploration of how do we get rid of the square root in certain problems. And so it can be a very finicky thing. So we are faced with the same dilemma. How do we get rid of the square root? And the answer is we just get rid of it. And you're probably thinking, oh, this is great. I love math. It's just like, hey, I don't like it. Okay, it's gone. Woo! Well, okay, it's not just a matter of like, well, if you don't like it, get rid of it. There's a little bit more subtle thing going on here. And it's important to understand why we can do things and why we can't do other things. So the reason why we can get away with taking the square root out is because the square root has a really nice property. So the square root function is a function which is increasing. If you want to be technical, it's monotonic. What it means is as we're moving from left to right, our square root is going uphill. So we're going uphill, moving from left to right. Well, how do we use that information? Well, it says if you want to make the whole expression big, make the inside part big. Because the further to the right you go, the higher up you go. If you want to make the whole thing small, make the inside part small. Because the further to the left you go, the smaller you go. So whenever you have a monotonic function and you're trying to say, well, I'm trying to minimize or maximize the expression plugged into a monotonic function, it says, okay, just work on that expression. Whatever does that will be what we need. Let's do one other thing. In addition to getting rid of the square root, let's make this look a little bit nicer. So let's pull out a root 2 over 2. So it's x squared. Now, if I pull out a root 2 over 2, what would I have? Well, I got the root 2, but the over 2, I don't have that. So I have x squared minus 8. All right, and if you squared that, we would have x plus 6 quantity squared plus 1/2, because root 2 over 2, if you square it, that would become 2/4, which is a half, and then x squared minus 8 squared. Good. Now, that's not so unreasonable. In fact, it's something we feel somewhat comfortable in making more progress on. Well, of course, because we have to make more progress. So let's give this a name. So here, we'll call it our function f of x. So that's what we're trying to optimize. So what is f prime of x? Well, that would be, take a derivative, 2 comes down, x plus 6 to the 1, times the derivative of the inside, which is 1. Then plus, well here, 2 comes down, 2 times a half is 1. And then you have x squared minus 8. And then, don't forget the chain rule, okay, times 2x. All right, so that's what we'd have if we took our derivative. So, clean this up. That would be 2x plus 12 plus 2x cubed minus 16x. Huh. Well, I mean, it is what it is, right? Okay. Well, let's see if we can rearrange this a little bit. So let's see, we have 2x cubed, and 2x minus 16x would give us what? Well, that would be minus 14x, and then a plus a 12. Okay, good. And now you're like, hey, it's a cubic. It's not a quadratic, it's a cubic. Is there a way to solve cubics like a cubic formula? There actually is. So, if this is the size of the quadratic formula, the size of the cubic is like this big. And the size of the quartic formula, oh my gosh, it's huge. And quartic means 4th degree, by the way. And the size of the 5th degree, it doesn't exist. There is no formula for a 5th degree. Whoa! There's a lot of beautiful math behind that. But that gets us sidetracked. We don't want to go that direction. So how do we approach this? Now, one thing we can see is that everything has a factor of 2. Since everything has a factor of 2, let's go ahead and pull out the 2 just to make us feel a little bit more comfortable. X cubed minus 7x plus 6. So probably the way we're going to approach this is say, maybe there's some low-hanging fruit, which is another way to say, maybe we can guess a couple of roots. And if we can guess, that gets us going. And oftentimes it's the getting the going, that's the hard part. Okay, so as we look, we say, well, try 0. 0 is always a good thing to try. And no, that's going to work because you end up with something 6. That's not 0. How about 1? All right, you get 1 minus 7 plus 6. Ah, that one's going to work. See, that'd be 0. Okay, so we have our great aha. So our great aha is our sort of observation that 1 is a root. Okay, so how does that help us? Well, once we know that 1 is a root, what we can do is say, well, that tells us it's going to factor a little bit as 2 times x minus 1 times other stuff. Now, what's the other stuff? Well, probably you can do some long division, or you can say, let me reason. Oh, let's do long division. We should practice that a little bit. It's good to practice. So x minus 1, divide that into x cubed. Now there's no x squared, so there's a 0x squared. That's a placeholder. Minus 7x plus 6. And the way long division works, of course, is you always say, look at the leading terms and ask, what would I need to do? X times what gets me to x cubed? Well, x squared does. So multiply this whole expression by x squared. X cubed minus x squared. Subtract. That leaves us with x squared minus 7x plus 6. All right, I have x. To get to x squared, I need to multiply by x. So plus x. X squared minus x. Subtract. The x squareds cancel. They have to. That's the design. Minus 6x plus 6. Well, I have x. To get to minus 6x, subtract 6. That's what I have to multiply by. Minus 6x plus 6. I subtract remainder of 0. But I knew I'd get a remainder of 0 because I knew that 1 was a root. So that is what goes here. Now, there's other ways to sort of reason a lot of it. You can say, well, I need to get to x cubed, so x times what gets me to x cubed? That's x squared. And on the end, I need to get to 6. Minus 1 times what gets me to 6? Well, minus 6. And then you have to sort of think about the middle one. But you can do things such as, well, say, minus 6x and minus 1 times whatever that is combines together to give you minus 7x, so it has to be a plus x. So that's a sort of an alternative way to sort of like probe around, and you can get there as well. Now, can we factor x squared plus x minus 6? We need two things that multiply together to give us negative 6, but that add together to get positive 1. Okay, I can see some good candidates. So this would be 2, there's x minus 1, and so if I do 3 and negative 2, right, because they multiply to negative 6, and they add to positive 1. And you can check x squared minus 2x plus 3x, that's the plus x and minus 6. All right. Okay. Wow. It factored. Beautiful. Beautiful. Okay. So now where are our possible roots? Possible critical points, which we need roots. In other words, that's where derivative is 0. Derivative is never undefined. It's a polynomial, so that's good. So we have 3 candidates. X equals 1, x equals -3, and x equals 2. So there's 3 places that it might be the closest. Now, logically speaking, we know which one it is. So we're going to go ahead and say which one is the best. Can you see it? It's got to be the -3. Because I'm over here at -6. I don't want to go all the way over to 1 or to 2, because that would have me go all the way across. It's easier to just go to like -1 or -2. So 1 and 2 are far away compared to other points. So -3 has to be our best answer. So our final answer would be -3, comma, right, square -3, that gets up to 9, so 9/2 root 2. Okay, but let's suppose we wanted to check and argue this with a test. Well, we could do a quick test here. To see that -3 is a minimum, well, what can you do? We can do our second derivative. That's not so bad to find that. What would that be? 6x squared minus 14. And if you plug in -3, you get 6 times 9, which is 54 minus 14. So f double prime of -3 is a positive number. Okay, so that means that -3 is indeed a minimum. If you plugged in 1, you'd get a negative number. And if you plugged in 2, it'd be back to positive. So in some sense, you could say, there's kind of this strange phenomenon is that you're getting close, you get farther, you get closer again for a while, and then you get farther again. So, all right, I think that's convincing enough. Okay, so there you go. Good. Good problem. Good problem. All right. Well, time for another problem. A long strip of paper, as shown in the figure, see, here's the figure, has width AB is 9 centimeters. So the distance from top to bottom is 9. A point P is marked on the lower half of segment of AB. So in other words, P, it's not high up, it's closer to B. That's what it means by the lower half of the segment. And the paper is then folded at P so that the upper left corner, A, ends up on the lower edge of the paper. So you see there was originally folded here, and then I creased it at P just so that the corner touched there. All right. The question, what is the maximum possible area of the shaded triangle that's formed? And of course, for full credit, well, okay, so this came from an old exam. You must give the maximum value of the area and demonstrate that your answer is indeed the maximum. Okay. Well, So let's think about what's true. Well, we can look at this and we say, what can we vary? Well, the thing that we can vary, we can't vary the size of the paper. That's fixed. It's 9 centimeters. So that can't vary. What can we vary is P. So the P is what we can move around. So P can move up and down. All right. Well, given that we can vary our value for P, we have to put a variable name somewhere into this diagram. So let's mark the distance down here. Let's call this X. All right. So far, so good. So that's X. Now, that means that this is X as well. Because the distance between A and B is 9, if this distance is X, what's this distance from A to P? Well, it's 9 minus X. All right. So here's the kind of the key point here. That distance 9 minus X also shows up somewhere else. So I'll use a different color just to highlight. So here's 9 minus x. This point from P to A folds over to here. So this side also has 9 minus x. All right, so now I have two sides of a triangle. And it's not just any kind of triangle, it's the right kind of triangle. So when I have a right triangle and I know the lengths of two sides, what do we do? Pythagorean theorem. So we apply Pythagorean theorem. So what do we have? This missing side. Well, let's give it a name, L. We know that, we can probably squeeze it here, that x squared plus L squared, x squared plus L squared, is equal to 9 minus x squared. Or, if we square that out, we get x squared plus L squared equals 81, then minus 18x, because that's the cross term, plus x squared. Well, we can cancel off the x squareds, and we get L squared is equal to 81 minus 18x. So, what does that say about L? Well, that says L is the square root of that. So, the square root of 81 minus 18x. All right, there we are. Now we have the sides of our triangles. And in particular, since we have the sides of our triangles, we can talk about the area of our triangle. Because remember, what are we after? Maximum possible area. Maximum is what's telling us that we're optimizing. Possible area tells us what we're optimizing. So we have that our area as a function of x is 1/2 the base square root of 81 minus 18x times the height times x. All right, and there we go. Now, we can proceed. There are things where we may want to say, can we get rid of the square root? There are actually ways to get rid of the square root, but for now, we'll just work with what we have. Okay, so let's clean this up a little bit to make it more friendly to take the derivative of. So 1/2 x, and we'll think of this as 81 minus 18x to the 1/2 power. So our derivative, a prime of x, would be, well, root of the first, 1/2. Then we have 81 subtract 18x to the 1/2. And then plus, so root of the first times the second, plus the first times root of the second. The 1/2 comes down. 81 subtract 18x to the minus the half, and then multiply by the root of the inside, so my minus 18. Okay, good. So the next thing for us to do is clean it up a little bit. So we can factor out, well, certainly we can factor out, there's a bunch of halves. Let's pull out a 1/2 for right now, and 81 subtract 18x to the 1/2. Negative 1/2. That's the smaller power. So from the first term, since I pulled out a negative 1/2, this was positive 1/2 to begin with, that'll leave us with 81 subtract 18x. From the second term, I grabbed the half. I grabbed this 81 minus 18x to the minus 1/2. So I'm still left with this 1/2, this minus 18, and that x. So if you put that all together, that's minus 9x. All right, well, what does that lead us to? Well, let's focus our energy over here. This is really 81 subtract 27x. Okay, now, where could we have problems? Well, certainly we could have a problem if this first part was 0 on the inside. So what would that be? Well, so we would have a problem here is if x were equal to 81 over 18, right? Because I can just move the 18x across, and then 81 divided by 18. Well, that's the same as 9/2. Now, where does that fit into our picture? So 9/2 is exactly the halfway point. So if you go at exactly the halfway point for P and fold, then the point A would end up exactly on top of the point B, what would our total area be? 0. We're not going to be able to maximize and get the answer to be 0 because we can see that we can get non-zero area. So this is not going to be the answer. In some sense, you can think of this as sort of the extreme case. And sometimes extreme cases are the right answer, so you have to check, but it's not in this case. So we say, all right, so we need to 81 minus 27x. If we set that to be 0, that says x should be 81 over 27. Well, that's also the same as what? That's 3, because 81 is 3 times 27. Okay, so here is our critical point. Good. Now, because we want to get the points, right? It says full credit. We want to get it all. Okay, what do we need to do? Well, what we need to do is show that, hey, this is indeed a max. So what can we do? Well, we'll do first derivative test. All right, so here we go. First derivative test. Here's our point 3. Now, suppose I plug in 2. Well, this is a positive. This will be positive. And 81 subtract 54 is positive. So that says our A prime is positive. So we're going up. All right, that's a good sign. We are looking for a maximum. Let me have said minimum a minute ago. Definitely this is a maximum. Okay. Now if we plug in 4, okay, positive. 81 subtract 72 is 9. Okay, that's going to be positive. 81 subtract 108 is negative. So the whole thing combined is negative. So we're going up, and then we're going down. So this says this is a max. Good. So we've now shown it is a max. We've demonstrated it. Now, we're not quite done because what haven't we done yet? We haven't answered what it was looking for. It's looking for the maximum possible area. We found when it happens. We said, aha, we want to fold it so that we're 3 centimeters along. So now we actually have to say what the area really is. So what is our maximum possible area? Well, we can put it in our picture here. We can mark. So that will have length 3. This side will have length 6. And then we have to do a quick computation here. 81 minus 18 times 3. Well, 18 times 3 is 54. 81 subtract 54 is 27. So it's the square root of 27. And by the way, that's the same as 3 times the square root of 3, because you can pull out a factor of 9. So our area is 1/2 base height. So our maximal area is 9/2 root 3. All right, good. And that's it. Now, I should mention in passing that I said there are ways to do this problem without having to deal with the square root. Here's how you could approach it to get rid of the square root. You could say, all right, let's not focus on optimizing A, but let's focus on something that, if we optimize, gives us the optimum for A. So one thing we can do is say, hey, let's make a nice little observation. Let's go ahead and pull out, since both of these terms have a 9 in them, let's pull that out of the square root to begin with. So this would be, if I pull a square root of 9 out, that would be a 3/2. And I'll put the x in front just to make it look better. And then I have the square root of 9 minus 2x. Now, here's the idea. I want to find something which, if I optimize, is equivalent to optimizing this expression. And what I'll optimize is a of x squared. So what would that be? Well, that would be 9/4 times x squared times 9 minus 2x. Well, in fact, I can do even better. Look, the 4 9ths, I can move that across. So I can say, look, 4 9ths times a of x squared is this other stuff, 9x squared minus 2x cubed. And here's the punchline. If I optimize this expression and find the optimum value, I will have also optimized this expression as well. And you'll notice this has a small advantage. There is no square root. And it's almost to the point where if you've been playing around with it, you can work out a lot of it in your head. And okay, so that's something that could have happened. We didn't explore it on this time, but, you know, who knows? Who knows? So, on to another problem. Of course. Of course. All right. Find the area of the largest triangle that can be inscribed in the unit circle with one vertex at 1, 0 and the opposite side parallel to the y-axis. Okay, I think we need a picture here. So there's a circle, not just any circle, of course, the unit circle. And so the unit circle we have centered at the origin. All right. And what do we have? We have inscribed, just means we're going to have the vertices be inside the triangle. One vertex is at 1, 0, which means our vertex here at 1, 0. The opposite side is going to be parallel to the y-axis. So the opposite side will probably be over here. And so here's our opposite side. And there we go. All right. All right, so far so good. Now, the question becomes, what are we trying to do? Well, we're trying to make it the largest. Aha, the est again. Optimization. That's how you recognize it. Look for words that end with est. Or, of course, think about how could I put in a word that ends with est. And that's going to be what tells me what to do. All right, so we need to start thinking. Now, of course, there's a couple of extreme cases. You can imagine that you could have something like over here, a really long and skinny triangle. That doesn't have very much area. We could also do something way over here, and boy, that's a terrible one as well. Very, very shallow. We got to somehow balance it. We're looking for that nice little sweet spot. Okay, so, what can we do? What can we do? Well, let's think about it. We could say, let's think about this point. Where is it at? Well, it's at the point, let's say the x-coordinate is at x, and then square root of 1 minus x squared. All right, so there we go. That's our location. Now, what is our height? Well, so the answer is the height. I'm going to think of my triangle as my base is this length, and the height is that length there. So the base will be twice square root of 1 minus x squared, because I'm going to have square root of 1 minus x squared is just this part, and then I'm going to have the part downstairs. So area is 1/2 the base to square root 1 minus x squared times, now the height is from the x here to 1 there. So it's the difference from 1 to x. So 1 minus x. 1 is going to be a larger value. So it's always large value, subtract small value. That's how you find the height. And this becomes, well, 1/2 times 2, square root 1 minus x squared times 1 minus x. Okay, well, now we have to take a derivative of that. We can make it a little bit easier on ourselves, because 1 minus x squared is what? Well, it's really 1 minus x, 1 plus x. And then I have 1 minus x. So if you think about what you really have is you have a 1 minus x to the 1/2, and 1 minus x, that's 1 minus x to the 3/2, and then a 1 plus x to the 1/2. All right, well, now we have our function. Single variable, we're ready to proceed. So, our derivative is a function of x. So we're going to take derivative of the first. So that would be 3/2, 1 minus x to the 1/2, and don't forget the minus 1, times the second, 1 plus x to the 1/2, plus the first, 1 minus x to the 3/2, times the root of the second, which is a 1/2, 1 plus x to the minus 1/2, and then times a 1 by the chain rule. All right, well, so let's pull out. What can we pull out? Well, we can pull out a 1/2. That gets rid of some fractions. That's good. The smallest power of 1 minus x is to the 1/2 power. And the smallest power of 1 plus x is to the minus 1/2 power. So if we pull all of that out, what are we left with? Well, we have a 3 there. We grab the 1 minus x. We didn't grab the minus, so that's a minus. And then we'll have a 1 plus x. All right? Good. And, well, the next part, right? Here, 1 minus x to 3/2. Well, pull out a 1 minus x. Okay. And because we pull out a 1/2. And then we got the 1/2. And then we got the 1 plus x minus 1/2. Okay, so that one is even easier. Okay, that's nice. So let's see. This last part here, minus 3x plus 1 minus x. So this become a minus 2 minus 4x. Okay, or if you pulled out a negative 4, pull all the way out to the front. Minus 4 times a 1/2 is minus 2. 1 minus x to the 1/2. 1 plus x to the minus 1/2. And because we pull out a minus 4, we'd be left with a x plus a 1/2. Okay, so we really have 3 candidates. And what are they? Well, we have x equals 1, but that's this little teeny tiny triangle right there. That's not going to work. No area. Here, x could be negative 1, but that's the little skinny triangle. No area. That's not going to work. Or negative a 1/2. That says, okay, go about halfway. Now that could work. In fact, it's the only viable one that's left. And therefore, that is the right choice for x. Now, that's not our answer because we're looking for the area, but now we know what to plug in. So we can say that our area at negative a 1/2 would be a 1/2 times 2, which is 1. Actually, we can come and use this form right here, right? So 1 minus a 1/2 would be 3/2 to the 3/2. Okay, and then 1 plus minus a 1/2, which would be 1/2 to the 1/2. And if you put that together, well, what do you end up with? 2 to the 3/2, 2 to the 1/2, 2 to the 4/2, which is 2 squared. So that's a 1/4. And then upstairs, 3 root 3. All right, so we end up with 3 root 3 over 4. Okay, all right, good. Let's do this a different way. Let's try this a different way. Because, of course, if we see unit circle, there should be something that pops up in the back of our mind. So unit circle, there's something that's nice to remember, and that is that unit circle is tied to trig. Okay, so how is the unit circle tied to trig? Well, namely, if I look at the points on the unit circle, what I can say is that any particular point has the form cosine theta, sine theta. All right, that's always true. So instead of thinking this as x comma square root of 1 minus x squared, let's think of it as cosine theta comma sine theta. So what do we need to do? Well, let's figure out what our various pieces are. So, what would we have? The height of the base would be 2 sine theta. So our area is equal to 2 sine theta. So that's our base. Our height, this length, well, that's still 1 minus cosine theta. And then that's all divided by 2. 1/2 base height. So we end up with sine theta minus cosine theta sine theta. Okay, so what we have to do is figure out how do you optimize this expression. All right, well, an interesting challenge. Well, we always like a good challenge, right? So cosine theta sine theta, what can we do with that? Well, I suspect at this stage, let's just take a derivative and see where we end up. On a side note, I've never done it this way before. This is going to be exciting. I have as much idea of what's to come as you do. So, woohoo! Let's find out. All right. So, a prime of theta. Well, derivative of sine is cosine. Then here, product rule. So, derivative of the first, derivative of minus cosine, is a positive sign. So, plus sine theta times sine theta would be plus sine squared theta. And then, okay, that's derivative of the first times the second. Then the first minus cosine times the derivative of the second, which is cosine. So that's minus cosine squared. So that's our derivative. Cosine plus sine squared minus cosine squared. Now, we want to figure out when does this equal 0. The problem is you have cosines and sines, which are like apples and other types of apples. They're not quite right. And so if we want to make progress, we'd like to get everything like a cosine or everything like a sine. Since we only have a single place where sine shows up and it's being squared, it's best to try to say, hey, let's rewrite the sine squared. So we can write this as cosine plus 1 minus cosine squared minus cosine squared. Or if you like, this is minus 2 cosine squared theta plus cosine theta plus 1. And now we say, okay, what can we do with this? Well, now we can try and factor. It is a quadratic. See, if you look at it, it's minus 2 times cosine theta squared plus the cosine theta plus the 1. So the cosine theta is acting as our thing that we're trying to factor. So here, what would we have? Well, what would we need? We'd have to have something. The 1, not a lot of ways to do 1. So that's 1 and 1. So we have to have something that multiplies together to give us minus 2 cosine theta squared. So multiplies together to give us negative 2, adds to give us 1. So that would be 2 cosine and minus cosine. And if you check, minus 2 cosine squared, 2 cosine minus cosine, so that's just a single cosine, and a plus 1 on the end. Which gets us to cosine theta is minus a half, or cosine theta equals 1. Now, the good news is, if cosine theta equals 1, we can spot right away the area is 0, so we know it's not going to be this option. That's out. Cosine theta equals minus a half. All right, what does that tell us? Well, is there a convenient angle where the cosine of that angle is equal to minus a half? And the answer is, well, there is a convenient angle. And that would tell us here that our theta, if you think about it, so cosine theta equals positive a half would be at pi thirds. So what you would do is you would go, think of it as minus half, you go pi, then back pi thirds. So that would be at 2 pi thirds. But more importantly, what do we have? Cosine theta equals minus a half. We also have that sine of theta would be equal to square root of 3 over 2. That's the sine cosine coordinate. And now, if you just work it out, you see sine, that's the square root of 3 over 2. And then you have 1 minus minus a half, which is 3 halves. So you have 3 halves times square root of 3 over 2 gives you 3 square root of 3 over 4. So there's a few small details, but you're basically right there. Now what you do is you say, okay, at the optimum, you know what cosine theta is, you know what sine theta is, and therefore you can plug it in and find the area. Okay, it works out. It works out. Is it easier or harder? I don't know. But it's different, and it's okay. We're getting into the part of mathematics where it's kind of fun in that there's multiple routes to get to the right answer. And sometimes that's good, and sometimes that's challenging. the reason we say sometimes it's challenging is, what do you do? Because it's not like there's one way. And the answer is you try something. So this is something I learned when I was a student. I had a great professor, and in one class one day they said, look, there's a very simple way to find the answer. It always works, always works. Step one is you try something. And then, if that doesn't work, try something else. But never give up. You might get stuck in an infinite loop, but you'll hopefully someday get the answer. All right. Well, on to a very big problem. This is one of my favorites. Now, it's going to take a while for us to digest this. Okay, so here we go. Last week, you sold some pipe to your best customer, Mario, who used the pipe to connect Peach's castle to Yoshi's island. Okay, so here's Peach's castle. Here's Yoshi's island. So Peach's castle is located on the edge of a large lake. So this is a lake. While the island is located by going 5 kilometers along the shoreline. So that's the 5 kilometers. And then 6 kilometers into the lake. Now there were 2 types of pipes used. One that can run along the shore, and a sturdier, and of course more expensive, version that can be used in the water. This week, Mario's brother Luigi is coming in to get some pipe for a different project. As you are preparing the bill, you realize you misplaced the cost of the pipe used in the water. Whoops. But you do recall the following 2 things. The cost of the pipe that runs on the shore is 100 gold coins per kilometer. And the minimum cost for Mario's project happened when the pipe went along the shoreline exactly 5/2 kilometer. So for Mario, it was an ideal situation for him to put it so exactly halfway. The transition went from land to water. All right, the remainder went in the water. Okay, so if W is the number of gold coins per kilometer for pipe that can be used in the water, determine W and the total bill for Mario. All right. Now, there's a lot for us to digest there. It's sort of like, Here's the crazy thing. This is a kind of a different optimization problem. Different in the following sense. We are not going to optimize things where we're going to find the optimum. Instead, an optimum has been given to us because we know the optimum. See, it told us this right here. It said that the minimum cost happened when we were at 5/2 kilometers. So we know when the minimum occurred. So what don't we know? Well, we don't have the information about what led us to the minimum. So in some sense, what we're going to do is instead of finding the minimum, we're going to say we're going to find the function that produced that minimum. All right, so we're just turning things around ever so slightly. It should make things a little bit more interesting. Okay, so let's proceed. So how do we begin getting a handle on this problem? Well, the good news is they gave us a little bit of help. They marked this distance here as x. So we'll mark a few more distances. Certainly if this is x, then this distance here would be 5 minus x, because there's a total of 5 kilometers, and here's x kilometers along the shore. All right, well that's a little bit helpful. In fact, we can continue helping ourselves here. See, if this here is 5 minus x, and this is 6, well notice I have a triangle. And it's not just any kind of triangle, it's the right kind of triangle. So what can we do? We can do Pythagorean theorem. All right, so let's figure out the length of this side. It would be the square root of this side squared, 36, plus that side squared, which is 5 minus x squared. All right, so that's the length of the amount of pipe that goes through the water. So you give us a value for x, we can say that's how much pipe needs to be used in the water. All right, well, let's proceed cautiously now. Okay, well, what can we do? We can clean up a little bit. 5 squared is 25. 25 plus 36 would make this 61. And then if we multiply that out, that would be minus 10x, and then a plus x squared. All right, so there's the length of the pipe that we're needing in the water. We know how much pipe we need on the land. So let's figure out the cost, because we had a minimum cost. So our minimum cost would be what? We have a cost function based off of x. Well, we take however much pipe runs on the land. Well, that's x times 100. So 100x. Okay, so that's our land pipe. Plus, however much pipe is in the water times W. See, we don't know W. See, W is what we're after. It's the number of gold coins per kilometer for pipe that can be used in the water. So W is some unknown number. And then times the rest of it, square root 61 minus 10x plus x squared. All right, so there is our function. Good. Now, what comes next? Well, the next thing is, that's what we're trying to find. What are we looking for? Well, we're looking for W, but we know something about this function. We know that this function is going to be optimized at the point where x equals 5/2. So that tells us that we know that 0 is going to be equal to c prime of 5/2, because that's going to be a critical point. So let's figure out what the derivative looks like. What is c prime of x? Well, first part, that's pretty straightforward. That's 100. Good. Plus, now, here, this last piece is something to the 1/2. So the w is a constant. The 1/2 comes down. The inside stays as is, 61 minus 10x plus x squared to the minus 1/2 times by the root of the inside, which is minus 10 plus 2x. All right. Well, now let's plug in 5/2. And let's hope that something beautiful happens. I suspect something beautiful will happen. I'm an optimist. I'm always optimistic that beautiful things happen, because people won't give us ugly problems. They'll give us beautiful problems. So let's see, we have 100. That's fine. W is a constant, still around. Half is a constant. Now, let's work through carefully here. 61 minus 10 times 5/2. Well, that'll be 61. We'll just go ahead and write it out. 5/2 will be times 10 is 50/2, which is 25. And then we're going to add 5/2 squared, which is 25/4 to the minus 1/2. Hopefully that simplifies. And then minus 10 plus 2 times 5/2. Well, that's minus 10 plus 5, which makes this minus 5. Okay, so we're going to have to spend a little bit of time on that piece right there. 61 minus 25 is 36? Yeah, 36. Okay, so this is 36. Now, what's another way to think of 36? Well, I want to think of it in terms of force. So 36 would be 144 force. Add that 25 force. 144 force plus 25 force, of course, gets us up to 169 force. Now, this is actually good news for us, because 169 is not just a random number. It happens to be a perfect square. Ha! It's like they planned it that way, because they planned it that way. So let's update what we have here. So we have 100 plus, we have minus 5/2, I'll put that in the front. And then there's this W. And then we have the square root of 169 is 13. Square root of 4 is 2. Be careful. See that minus? That's going to flip things upside down. So that'll become a 2 over 13. Okay? So that's the 169/4 to the minus a half. Aha, the 2's cancel. Good. So we end up with, this is 100 minus 5/13 W. All right, now that's what we have. Remember, that equals to 0. So we can say that says that 5/13 times W is equal to 100, or W is equal to 13/5 times 100. Well, 5 goes into 100 20 times, which brings us up to 20 times 13 is 260. All right. Well, pretty pricey, but you know what? If it does the job, then, you know, we pay the bill. That's what we need to do. Okay, so we're almost there because what have we done? We've found W. That was it. So this is W. 260 equals W. All right. But remember, there was a second part. We want to find the total bill for Mario. Okay, but now that we know what W is, we can say what the total bill was. Because we say, aha, we plug in 5 halves. So that's the cost of 5 halves, which is 100 times 5 halves plus this 260 times, well, this expression, the square root of 61 minus 10 times 5 halves plus 5 halves squared. And you're probably thinking like, we got to do that again? Well, no, we already did it. See, we did it down here. This is what happens when you plug in, 5 halves into 61 minus 10 times x plus x squared. So we're not going to do it again. We're just going to say, this simplifies to 169/4 on the inside, and the square root of that would be 13 halves. Okay, well, that's good news for us. All right, now, what can we do? Well, 2 goes into 100. That would be 50 times 5, which is 250. Then 2 goes into 260, which would be 130 times 13. Well, 130 times 13, ignore the 0. It's 13 times 13 is 169. So this is 250 plus 1,690. And if you put those two numbers together, you end up with 1,940. And what's our cost? Well, things are measured in gold coins. So that is how much it costs for Mario to put in that pipe. Well, of course, Princess Peach and Yoshi, they're good friends to Mario. He'd be happy to pay that. All right, good. What a problem. What a problem. Now, one of the things that makes this intimidating, there's sort of two things. One is like, you see that wall of text, and you're like, I have to read that much? But the other thing is that it's turned the problem around. And that's one of the things we want you to get to, is to the point where it's not like, I'm going to learn 20 algorithms, and anytime I need it, I'll just find the right algorithm, and there I go. What we want you to be able to do is take the problem and think about things in different ways. It's like, okay, here's the starting point. Can you get to the ending point? Well, all right, here's the end. Can you tell me about something about how you started? That ability to transform problems, that's when you start developing that really useful and really valuable problem-solving skill. Oh, what a great problem. This will be one of the best problems I ever wrote. Maybe not the best. There's another good one coming up in a later session, but okay, it's a good one. It's a good one. This brings us, believe it or not, to our last problem. Boy, it's been a good ride. Well, let's hope it's a good one. So, determine the value of b greater than 0 so that the maximum area of the triangle whose sides are formed from the tangent line to y equals e to the minus bx at x equals a for a positive, the x-axis and the y-axis is 1. So the initial thought when seeing this is, what? Okay, so there's a lot to figure out what's going on here. So what we have is we really don't have one function. Rather, we have a whole range of functions. And they're all very similar to each other. So it's the variations of the exponential function. So here's this sort of family of functions. And our goal is to pick just the right one from that family. Now, the good news is they all have a very similar look, and that they all look like exponential functions. In particular, you might call this things that are exponential decays, which are going down. So let's sketch what a typical thing looks like. So here we go. And now what's going to happen is I have my exponential function coming along and doing this. So here's the y equals e to the minus bx. Now, let's suppose for a second, let's not worry about b. For now, let's just take b as a given. The next thing we say is, what's happening? Well, we're going to take the tangent line to this curve at some point a. So let's say this is a. All right, so we take this tangent line, and there we go. There's our tangent line. So the tangent line, there's going to be a triangle formed from the tangent line. And where is the triangle going to be? Well, it's going to be the tangent line, the x-axis, and the y-axis. So here's our triangle. Okay, so this is the triangle. And our goal is we want to make the maximum area of this triangle as, well, first off, we want to maximize the area. Then ultimately, we're going to say, hey, how do we make it so that that maximum area is 1? So first step, let's try to just maximize this area. So if we're after the area, then what we need to do is figure out what's in the area of this triangle as a function of a. So, how do we do that? Well, let's just think about our tangent line. In general, we have our tangent line would be y equal to our function at a minus f prime of a times x minus a. So, in our case, our function, this is our f of x, e to the minus bx. So, we would have, if I plugged in a, it would be e to the minus b times a. What is our derivative? We should do that. That would be minus b e to the minus bx. Okay, that's our f prime of x. So minus minus b, so that's plus b e to the minus bx. Oh, whoops. This is, why did I put a minus there? That should be a plus. Okay, so plus, so there's a minus going there. All right. And then that's times, times a. I am so sorry. Okay, back on track, So e to the minus ba, subtract. Let me just rewrite this whole thing. And then we can pretend like I never wrote it. Okay, so the function at a, so I'm plugging a in, e to the minus b times a, plus the derivative at a, which is minus b e to the minus b times a, times x minus a. Now, we want to know two things. We really want to know, where do I hit here, in other words, the y-intercept, and where do I hit there, the x-intercept? Now, you might want to say, well, why do I want to know those two things? And the answer is because we're after the area of a triangle, and so what I really am after when I'm looking for these values is something that I can call the height and something I can call the base. So the x-intercept and the y-intercept are going to be my height and base. Okay, so let's find the y-intercept. That's the easy one. So y-intercept would correspond to when x equals 0. So we get e to the minus ba. And then here, this is 0. There's a minus a. So minus a times that. So that's plus ab e to the minus ba. Or if you like, that would be 1 plus a times b e to the minus a times b. All right, we can write it that way. Yeah. Okay, so that's the y-intercept. How do we find the x-intercept? Well, the x-intercept is very similar. The only thing is, instead of having our x be 0, we're going to set y equals 0. But otherwise, the process is the same. So x-intercept, that says y equals 0. So we get 0 equals e to the minus b times a minus b e to the minus b times a times x minus a. Now, the good news is we can do a quick simplification, and that makes our life a lot better. Notice that both terms have e to the minus ba. And we know e to the minus ba is never going to be 0. And the reason we know that is because it's e to something, and e to something is never 0. So those we can knock out. So what do we have? Well, we get the following. This is really equal to 1 minus b times x minus a. All right, so we rearrange. And we can say, well, that's really the same as what? 1 equals b times x minus a, or x minus a equals 1 over b, or x is equal to a plus 1 over b. And if we wanted to, we could even rewrite that. That's really what? It's really ab plus 1 all over b. So we can do that. Okay, so now back to our regularly scheduled problem. For the time being, b is fixed. I haven't said anything about b. It's the a part that's varying. So this is one of the things that makes this problem fun, is there seems to be two things in play, a and b. So for right now, we say, okay, fix b, hold it as a number, and perturb a. So now we head back in and say, what's our goal? The area of our triangle. So our area, we can say as a function of a, so our area as a function of a is 1/2 our base, that's the distance from 0 to our x-intercept, so that would be ab plus 1 over b, and then our height, which would be, our height is here, which is, well, again, it's really ab plus 1 e to the minus ab. So there we go. That's our area. Okay, well, we can rewrite this as what? That's 1 over 2 times b times ab plus 1 quantity squared e to the minus a times b. Now, what comes next? Well, the next thing for us to do is to take the derivative, because we're trying to optimize area. We can see that we're trying to optimize area, the maximum. So now we're going to say, all right, take the derivative. So we're going to look at what we could call area prime, right? The derivative of area prime. So what is that going to be? And remember, what's varying? A is what's varying. So we have a product rule. So we have, all right, the 1 over 2b, and then the 2 comes down, times ab plus 1 to the 1 times the derivative of the inside with respect to a, which is b. And that's e to the minus ab. Okay, so that's the derivative of the first times the second. So this b comes from the chain rule. Plus the first, 1 over 2b, ab plus 1 quantity squared, times the derivative of the second. Well, e to the minus ab, and then the derivative of minus ab with respect to a is minus b. All right, things simplify. Okay, so let's make a note about what things simplify. So certainly we can cancel some b's. That's kind of nice. Makes it a little bit easier. So those b's cancel. In the first term, we can cancel a 2. That's pretty good. We can also factor stuff out. So let's see what we can pull out. Let's pull out, both terms have ab plus 1. Both terms have e to the minus ab. And let's go ahead and pull out a single half so that there's no fractions left inside. So 1/2 ab plus 1 e to the minus ab. And now, what does that say? Well, what's left? Now, the first term, I grabbed everything except there wasn't a half to grab. So, since I need to compensate for that half that's being pulled out, that'll be a 2. Okay, cool. Now, the second term, I did grab the half, but I only grabbed one of these ab plus 1s. I did grab the e to the minus ab. I didn't grab the minus, so I don't forget that. So that'll be leaving with 2 minus, and then we have ab plus 1. All right, well, that's what? That's 1/2 ab plus 1 e to the minus ab, and then that'll be, when we take 2 minus ab plus 1, the minus goes through, so 2 subtract 1 makes 1 minus a times b. Now let's think about our pieces here. As we go through and look at our pieces, we say to ourselves, do I need to worry about the ab plus 1? Could that be a place where I get 0? And the answer is no. How do we know? Because both a and b are going to be positive. So we've been told that a and b are positive, so there's no way ab plus 1 could be 0. Okay, so don't need to worry about that part. The e to the minus ab, that's never 0. It's never undefined. So, lo and behold, when we're looking for a critical point, the only place we have to look is the 1 minus a times b. All right. Now, what does that say? Well, that tells us that we really need a times b to equal 1. And for the time being, let's remember what our current varying thing is. That means that we're varying a. So the optimal choice is to select a as 1 over b. Okay, so for a fixed value of b, if I'm trying to figure out where a should be, I should pick a to be 1 over b. So that says as I change my function, I change where I should be taking this line of tangency. That makes sense. It's a reasonable thing to say. But now how do we get to our next stage? Well, let's now plug this new parameter we found, this a equals 1 over b, back into area. Okay, so what is that going to give us? So it says, so given b, the max area will be our area at 1 over b. In other words, the result when you plug 1 over b in. So let's plug 1 over b in. What do you get? Well, you get a 1 over 2b, because that doesn't involve a at all. And then here we have a times b plus 1. But a times b is going to equal 1. So that's 1 plus 1. And so that's really 2 squared. And then it'll be e to the minus ab. But again, that's minus 1. Now, if you clean this up, what do you end up with? Well, you can cancel off a single 2. So you get 2 over b, and the e goes downstairs. So there we go. So if you give me b, I can now tell you, hey, the maximum area that you can form here is 2 over b times e. Okay, so great. How do we find the answer? Okay, so now after we've done all that work, hopefully it's useful. We step back and say, what is it we're looking for? We're looking for the value of b. See, that's our goal, determine b. So that the maximum area, and then there's a lot of, is 1. So we want the maximum area to be 1. That's what we want. Well, we just found the maximum area. It's 2 over b times e. And therefore, if we want it to be the case, the maximum area equals 1. So we need 2 over b times e to equal 1. Well, now multiply the b across, and we can say that b should be equal to 2 divided by e. And that's it. Wow. Cool. Amazing. Amazing. And I'm so serious, like, wow, that really is amazing that we can do this. This one is definitely on the harder end. So that's why we saved it. You always save the best for last. The last couple were definitely more challenging. All right. Well, if you started at the beginning and you made it all the way here, congratulations and thank you. Hopefully, you didn't fall asleep. I hope you picked up some things along the way. And for making that commitment, I wish I had something more profound to say. But what I do want to say is, I know that these are not the easiest things to think about. There's a lot of hey, there's a lot of things coming into play. There's this is changing and that is changing, and how do I put it all together? But I believe in you. I believe that you can learn how to solve these problems. It comes with practice. Put in the time. Put in the effort. You can do this. You've got this. So good luck, and thanks for coming and staying so long.